Alright, this is the last review session. So you're going to look at light and matter. So, start of the topic, we were talking about different types of light, different sources of light, and the variation that they have. Really the only thing just about of use to us from our Units 2 work was the equation C equals F lambda. From there, it's all extension looking at light in terms of whether it's acting as a wave or whether it's acting as a particle, and what the evidence says to say one way or the other. So in order to do that, we looked at the different types of sources. So there are a couple of types of source of light that we could get. Sunlight, less relevant the longer we go on. Incandescent light bulbs and light from candles. And what we were talking about was the temperature radiation curves and how temperature related to the wavelength. So, excuse me, red equals cooler temp. So if the light's more at the red end, then it suggests that the object is at a cooler temperature. If we're more towards the blue end, then the object's at a much hotter temp. And so we get sort of this radiation curve, something like that, where the peak perhaps may be in infrared or red, where it's a cooler object, and then if we've got a hotter object, then that peak gets shifted Okay, now probably most important to us in terms of light was an understanding of coherent versus incoherent. What we mean by the term coherent is that the light is in phase, so all the wavelengths align, and we're talking about a very similar, if not exactly the same, wavelength. So variation of maybe 1 to 2 nanometers. When it's incoherent, light can be in any phase and light is at any wavelength, which is what all of these are here. If we're talking coherent, we're pretty much predominantly talking about light that's going to be coming from a laser. So we've been told all along light is waves. We emphasised that in year 11, looking at the wave properties of light. And then the first thing that we really looked at was diffraction as a major support. We discussed reflection and refraction briefly, but the real new content came with diffraction. Now, this is the main evidence that we were observing, and for diffraction to occur, we need lambda to be proportional to the slit width. And when that is the case, we see waves come in, and then as they pass through the gap, we get this spreading out effect. Okay, so this understanding of diffraction and how light spreads out, waves spread out, pave the way for explaining Young's experiment. So if light was particles, then what we would have expected from the double slit experiments is light coming in. It would have passed through the double slit, and then on our screen we would have expected two bright spots. But this is not the case. So what was observed is the coherent light coming in, passing through the double slits, and we saw on the screen multiple bands, multiple bright spots, with the brightest occurring at the central spot, the central maximum it's called. So the interpretation of these observations is the key here. Okay, this demonstrates wave interference. You can pretty much guarantee a question on this. Explain how this observation demonstrates light as a wave. Okay, you're pretty much betting on that being there. So you can have something on your cheat sheet ready to go that you can adapt to the question. So don't just necessarily copy it straight off your cheat sheet, but have it there so that you can adapt it to the keywords in the question. So how is it demonstrating? So as the light passes through each slit, it diffracts. The diffracted waves interfere constructively and destructively to create antinodes and nodes on the screen respectively. Okay, so the antinodes are your bright spots. I know it's got the word anti in it, and that makes you think of something destructive, but it's actually the other way around. Another fairly typical question that you'll get will be around path differences and being able to calculate a wavelength from a path difference, or determine the path difference if we know the wavelength. So they'll show you a central maximum and say to this dark spot or this bright spot how many path differences, or what's the wavelength, or something to that variety. So path difference. If it's an antinode, that is a bright spot, path difference is n lambda. N equals 0, 1, 2, 3, so on, where 0 is your central max. Okay, so they both travel exactly the same distance to get to the central max. To the next bright spot, one of them has to travel one whole wavelength further than the others. For the destructive interference, or for nodes, path difference equals n minus a half lambda, where n starts from 1, the first blank spot, the second blank spot, the third blank spot, and so on. Okay, factors affecting the diffraction pattern. That is the distance or the separation of the antinodes. Now, strictly speaking, this isn't on the course, but it's the most useful thing that you can whack on your cheat sheet. Delta X equals lambda L over D. So delta X is the distance between antinodes. And what this equation tells us, or gives us, is a really quick reference. So we've got increase lambda equals increase in delta X. Anything that's on top is going to increase the size of the separation. Anything on the bottom will decrease it as it goes up. Okay, so L, that's the distance to the screen. So by increasing the distance to the screen, then delta X goes up. And then D is your slit separation. So by increasing the slit separation, you actually bring the pattern closer together. So you need a smaller slits to get a larger separation pattern. You two right? And single slit separation. So this is where we're passing light through a single slit, and then we get a pattern appearing on the screen. Something like that, with the main bright spot will be obviously opposite the slit. Now, in this one, basically the light is effectively interfering with itself as it comes through. So if we look at this in terms of rays, light coming through on the angle, as it passes through here, what we're saying is, if we draw the line perpendicular, we've got a whole wavelength more there than it's travelled down here. So wavelength 1 is going to interfere with wavelength 2. So this will be on given angles as that light passes through. Yeah, and here lambda must be proportional to slit width, of course, and same deal with the wavelength. The larger the wavelength, then the greater the separation pattern that you're going to see. So red light's going to give you a greater separation pattern than blue light. Obviously, putting it further from the screen will give you a greater separation. Okay, so that was light as a wave. That's the main sort of area that we looked at, evidence of light acting as a wave. So we then moved on to the next discovery of the photoelectric effect. This then started to turn the tides back towards, hang on, light's exhibiting behavior as if it's acting like a particle. So let's define photoelectric effect first. That's the ejection of photoelectrons from a metal surface. When light of a high enough frequency shines on it. So by definition, high enough frequency shining onto a metal surface, we get enough energy to emit or eject an electron from that surface. So it depends on obviously the frequency of the light that we're using and the type of metal that's being used. So intensity of the light is not going to affect whether a photoelectron gets released or not. What did intensity do by increasing the intensity? Yeah, increase the current. All it resulted in was more electrons getting ejected. Okay, so that, I guess, brings us to F0, which is the threshold frequency. And what that is the minimum frequency to eject a photoelectron. Light below this below this threshold frequency for this particular metal, does not release any electrons, regardless of how much intensity you bring. And this is where it starts to lead into this concept of, or proof of, the particle model. So energy of a photon is equal to hf. H is Planck's constant, which is 6.63 times 10 to the negative 34, and that's units, I think, or joule seconds or something like that. So that's in the joule second something or other. And then we have 4.14 times 10 to the negative 15 when we're working in electron volts. So depending on the units in the question, depending on the information you're given, as to which version of H you want to use. If the question is related to stopping voltage, anytime we've got voltages included, then H as electron volt seconds is definitely the direction that you want to take. Now, let's say EK max, which is a half mv squared, we know from motion, is equal to E V naught. So the early investigations looked at this V naught, this stopping voltage. And that is putting a reverse voltage onto the circuit to see how much energy, how much electrical energy it was required to stop the electrons that were being released, the most energetic electrons that were being released, and then in that sense working out how much kinetic energy that those electrons would have. So you can expect that there's a good chance that you'll see a graph like this, or you may actually have to sketch a graph like this, where we've got, well, for some particular light at frequency 1 at a given intensity, we get a sketch like that. We get current, so at intensity 1 it requires that much voltage. If we increase the intensity, we don't change the stopping voltage. What we do is just release more electrons, therefore we get more current flowing. If we change the frequency of lights, if we go to a higher frequency and therefore higher energy source of light, so we go to F2, where F2 is greater than F1, so it's a higher energy, then given the similar intensity, we're going to release the same number of electrons, but it's going to release it with more energy. Therefore, it requires a greater stopping voltage. So how does this provide proof of a particle model? So, a couple of things. F0. F0's a big one. Only light with sufficient energy releases electrons. And this is important. This occurs regardless of intensity or time that it's left shining on it. So leaving it on longer if it's of lesser frequency lesser than F0, or turning the frequency lesser than F0 on really high, it's not going to release any photoelectrons. The other thing that we can also say is that increasing intensity only changes the number of electrons, not the kinetic energy of the ejected electrons. So the way that this was then explained is that light's made up of photons. Each packet of energy, each photon, which is just a little discrete packet of energy, has a discrete amount of energy to give away. So the intensity just means we're adding more photons. So increasing the intensity means more photons, therefore more electrons are released. So that brings us to the kinetic energy frequency graph. Definitely expect a question on this in your exam. We've got frequency, usually times 10 to the 14, and we've got energy. Now this can be in times 10 to the negative 19 joules, or it could also be in electron volts. Now on here we get, for a given intensity, given metal, so for metal X, what we find is, key things on this graph, F0, threshold frequency, minimum energy required to actually release an electron. At this point, at the threshold frequency, it's enough energy to release the electron, but it has no extra energy, so it can't actually physically escape. We've got the work function. This is how much energy is required to be given to the electron to allow it to be released. And then anything above that, so if we go above the threshold frequency, anything above that will give us the amount of kinetic energy or maximum amount of kinetic energy that one of the ejected electrons can have. So we can summarize that in an equation. For a given photon, what it's going to give, so we've got the photon equals hf. It will supply the work function plus whatever's left will be kinetic energy. So if we look at the photon at this given frequency, so we've got a photon here at this given frequency, it's made up of the work function plus the kinetic energy. All of that energy has to be passed on. Alright, so photon momentum. So momentum is mass times velocity. We can rearrange that to be E over C, and that's because E equals mc squared, which is equivalent, or mass times velocity squared over velocity, would give us mv, so it's the same as E divided by C. Rearranging that, we know E is hf over C. F over C is the same as 1 on lambda, so we've got h over lambda. So we've got multiple different equations here that we can use and we can manipulate and vary depending on what the question's asking or what information we're given. Okay, important here that the particle obviously must be moving quite fast, and a particle needs to be very small. So the conclusion at this point was that, well, light acts as particles sometimes, light acts as waves at other times, never at the same time. So therefore, it must consist of a dual nature. Matter waves. The question then followed on was that if waves have momentum properties, can particles then behave like waves? So waves are behaving like particles. Can we have the reverse? Can particles begin to behave like waves? So we had lambda equals p over C, which is H over mv. Okay, mass can easily be measured, velocity can be easily measured. So quite easy to then substitute in and give a theoretical lambda. But it must be a very small particle, it must be moving very fast. Okay, final section. Actually, no, there's two final sections. So this is the second last final section. We have emission and absorption spectra. Definitely going to appear on your exam. So the basis for this is that each atom emits and absorbs a unique set of spectra. When we use the term spectra, we're just talking about wavelengths of light. So unique set, only exact values of energy. So all others pass through. Okay, so it's got to be something that's related to the atom, and it's basically the idea of shells didn't exist at this stage, but it's got to do with the energy levels that these electrons occupy. It's got to be an exact difference between these levels. So, you know, if we wanted to put a mathematical equation to it, so we'd say E equals HF, and that must equal EM minus EN. So the difference, the exact difference between two energy levels. Typical questions often give us things like the ionization level, then other shell levels. Let's just make up a few values here. And give us one more, minus 8.3 volts. So this here, sometimes written as N equals infinity, is the ionization energy level. Okay, that's the point where the electrons are going to be released. So we've got N equals 1, N equals 2, N equals 3, N equals 4. Now, difference in terminology. N equals 1 could be referred to as the ground state. The second energy level is the first excited state. N equals 3. Third energy level is the second excited state. So excited state means it's absorbed a photon and it's jumped up to a new level, not the normal level that it would be sitting in. So if it's going to absorb an electron, a photon, it has to be that exact difference. Okay, it can't just say it's at the ground state and there's an energy 4 electron volts. Should be EVs. So we've got 4 electron volts, that would jump it up to negative 4.3. That's more than the energy level. That would actually take it above. It can't absorb that extra bit of energy, or can't just leave that bit of energy somewhere, so that wavelength is going to pass straight through. It's only the exact difference that it's going to absorb. Another question they do like to add or ask is, I've seen it on a couple of times, draw in, if it's at the third excited state, what are the possible wavelengths that could be emitted as it falls back to the ground state. So you have to be able to stay 1, 2, 3. You've also got 4, you've got 5, and you've got 6 possible scenarios there, or 6 different wavelengths that could potentially be emitted if that was to fall, depending on whether it fell from the 4th energy level straight to the 1st energy level, or if it fell to the 4th, to the 3rd, to the 2nd, to the 1st, or the 4th to the 2nd, to the 1st. Those are the possible wavelengths that could be emitted. Does that make sense? Okay, sometimes you're asked to find the values, sometimes you're asked to draw in the possible, photons that would be released as that electron fell back through the energy levels. Okay. The last thing then is this concept of standing waves. And this, again, kind of helped to explain this concept of energy levels. So, electrons orbit only where levels form a complete standing wave. This is one of those ones that you can kind of just whack straight on your cheat sheet and adapt to the question. A diagram's also really useful in helping with your explanation. So say, here's your energy level. You got this standing wave going around. In this case, it's incomplete. Because the wave doesn't, or isn't complete, we get destructive interference. And the destructive interference basically says, collapses it. It cannot exist at that point. Okay, therefore, cannot exist here. So only energy levels that give us a full. Now let's see, how well can I do this? Let's go with 4. Give us a complete standing wave are going to exist. So it can effectively oscillate. Think kind of like a guitar string vibrating backwards and forwards around that energy level. Okay, so it's stable here, and it can occupy this level. Okay, equation that will go with that is n lambda equals 2 pi r. So we want to work out the radius, then it depends on how many wavelengths are going to be, how many standing waves are going to exist at that wavelength. Now if we needed to take that further based on other information, lambda does equal h over mv, so we could substitute that and you get n h over mv equal to 2 pi r. Very rare that you're ever going to see a question that goes into that sort of maths on that section of the question. Usually it's an explanation question. A lot of the questions in this section are explanation questions. Alright, that is it. So that's review done. Time for some exam papers.